welcome to The Explainer. Today, we're going to break down the force that powers, well, pretty much everything around us, electricity. We're going to trace it all the way from a single, tiny spark to the fundamental laws that make your phone, your lights, and your whole world work.
So, here's the plan. We're building this thing from the ground up. We'll start with the spark itself, then we'll get into the flow, feel the push that gets it all moving, and then meet the opposition that tries to slow it down, all before we get to the one golden rule that ties it all together.
All right, let's dive right in. At the absolute heart of every single electrical thing, I'm talking lightning bolts, text messages, you name it, is this one tiny fundamental property of matter called charge. Just think of it like an invisible force that makes all of electricity happen. It comes in two flavors, you could say, positive and negative. And the rule here is super simple, just like magnets, right? Opposites attract, and similar charges want to push each other away.
So how do we actually measure this stuff? Well, scientists give it the symbol Q, and the unit we use to measure it is the coulomb. It's named after a physicist, Charles Augustin de Coulomb. Now, what happens when all these little individual charges stop just sitting around and start to get organized and move together? Well, that's when things get really useful. That group movement is what we call electric current.
To put it really simply, current is just a stream of charges flowing through something like a copper wire. And it's not just about them moving, it's about the rate they're moving. You know, how many charges are passing a certain point in a certain amount of time.
And check this out. Here's a fantastic way to remember the formula that connects charge, current, and time. The source material for this explainer has this clever Hindi mnemonic, Q-I-Thi. It sounds just like Q, I, and T, and it translates to, why did she come? It's a surprisingly dramatic little trick to remember that charge equals current times time.
We measure this flow, this current, using the symbol I, and its unit is the ampere, or as most people say, an amp. To give you an idea of what that means, 1 amp is 1 coulomb of charge flowing past a point every single second.
Okay, here's a fun little quirk in physics. For reasons that go way back in history, when we draw our diagrams and do our math, we use something called conventional current, which we say flows from positive to negative. But in reality, the tiny electrons that are actually carrying the charge, they're moving in the exact opposite direction. Kind of weird, right?
So, we've got current, which is moving charge. But here's the thing. Charges don't just move on their own. They're actually kind of lazy. They need a push to get going. And in electricity, we call that push potential difference.
A really good way to think about it is like electrical pressure. You know, take a battery. It doesn't create new charges. It just provides the push, the potential difference that forces all the charges that are already sitting in the wire to start moving. And you guessed it, our source material has another awesome mnemonic for us. This one helps you remember the relationship between work, voltage, and charge. The phrase, wait, whoa, Q, sounds out W, V, and Q, and it translates to, wait, why that? It's another one of those clever little tricks to lock in the idea that work equals voltage times charge.
We measure this electrical push in volt, which is a term you've definitely heard before, right? When you talk about batteries or wall outlets. And it makes sense that we represent it with the symbol V.
Okay, so we've got voltage that's pushing the current forward. It kind of makes sense that there'd be something pushing back, right? And that opposition to the flow is what we call resistance.
Resistance isn't some kind of mysterious force. It's really just the result of all the moving electrons constantly bumping into the atoms inside the wire. All those little collisions create a sort of electrical friction, and that's what slows the current down.
And resistance isn't the same for every wire. I mean, think about it. A longer wire means there are more atoms for the electrons to bump into, so resistance goes up. A thicker wire is like a wider hallway. It gives the electrons more room to flow, so resistance goes down. And of course, the material itself matters a ton. That's why we use copper for wires. It has low resistance, but we use something like tungsten in a light bulb filament because its high resistance is what makes it glow.
We measure this opposition using the symbol R, and its unit is called the ohm. You'll see it written with the Greek letter omega.
All right, it's time to put all the pieces together. We have the push, that's voltage. We have the flow, that's current. And we have the opposition, that's resistance. Now let's see how they're all connected by one simple, elegant, and super powerful rule.
This is the big question. If you can understand this relationship, you can pretty much design any circuit you can imagine. And the guy who figured it out was George Ohm, way back in 1827.
And the answer is just beautifully simple. If you increase the push, the voltage, you get more flow, more current.
If you double the push, you double the flow. It's a direct, predictable relationship, as long as that resistance doesn't change.
This all comes together in one of the most famous equations in all of physics: voltage equals current times resistance, or V equals I times R. It's so powerful because if you know any two of those things, you can always figure out the third.
This direct relationship also gives us a really clear picture. If we were to plot voltage on one axis and current on the other, for most materials, we'd get a perfectly straight line. And the steepness of that line, the slope, that directly tells you the resistance. The steeper the line, the higher the resistance is.
So, let's wrap up the essentials. Charge is the basic stuff. Current is that stuff moving. Voltage is the push that gets it moving in the first place, and resistance is the friction that tries to stop it. And Ohm's law? Well, that's the simple, beautiful math that describes their whole dance.
That simple rule, V equals IR, is working right now inside the very device you're using to watch this. It governs everything, and understanding it is really the first step to answering an even bigger question. How do we take these simple principles and combine them to create the complex, amazing technology that basically shapes our entire world?